Welcome to this session of chemistry, electrochemistry. I am Mrs. Padma from Cloud Tutors. Whenever the word electrochemistry comes into the aspect of learning or teaching, we have to understand that this term of electrochemistry is involving two changes. One could be the chemical change and the other could be the electrical change. So there are some energy conversions happening during the process of electrochemistry. You can see here, and zinc rod is immersed in zinc sulfate solution. Copper rod is immersed in copper sulfate solution. And when these two half cells are connected by means of what is called as a salt bridge, then immediately you see after some time the bulb starts glowing when it has been connected by means of a proper electrical circuit. So how is this electrical bulb glowing? It is just because there has been chemical reactions that has been taking place in the two half cells, and because of which that chemical energy is able to give you what is called as the EMF of the entire cell, which is called as electromotive force of the cell. And that particular chemical energy, if you see, subsequently is getting converted into what is called as the electrical energy. If we look into the various aspects that are going to be duly covered in this chapter, are going to be introduction, electrochemical cells, and galvanic cell, and if time permits, I'll be stepping into Nernst equation in today's session. Of course, the remaining concepts will be conductance, electrolytic cells, batteries, fuel cells, and the last concluding part is all dealing with the various aspects of corrosion. So let me just step into the introduction aspect. Whenever we talk about electrochemistry, we do come across certain metals that we use in our daily life. So how do you think generally metals are being extracted? So are the metals produced by electrochemical methods? Of course, there are the principles of electrochemistry involved whenever metals are being produced by the various electrochemical methods. Now, the next question arises. Does the neurotransmission of sensory signals have electrochemical origin? Definitely the answer is yes. The neurotransmission of the entire sensory signals, if you see throughout the human body, it is all dealing with electrochemistry. So let's make an earnest attempt to first understand what is meant by electrochemistry, as well as the applications. Where are we using these principles of electrochemistry in our day-to-day life? Electrochemistry is the study of production of electricity from energy that is being released during spontaneous chemical reactions. And the use of the electrical energy is to always bring about what are called as non-spontaneous chemical transformations. To be very brief, let me tell you, the short scientific representation of electrochemistry could be just represented in this format of chemical energy getting converted into electrical energy. You can see the arrow mark which is towards both the sides. That means there are going to be changes happening wherein chemical energy is getting converted into electrical energy, there will be certain cells where you will see electrical energy being converted into chemical energy. That means they are all involving electrochemistry, especially the two energy changes. Now, let us see where are we able to apply the principles of electrochemistry. Of course, in the field of corrosion, organic electrosynthesis, industrial electrolysis process, energy conversion, energy storage, as well as sensing, they are all happening only by following the principles of electrochemistry. Many metals, if you take up, iron, copper, zinc, and so on, or even certain chemicals such as sodium hydroxide, caustic soda, NaOH, chlorine, Cl2, fluorine, F2, and many other chemicals, if we see, they are all produced by these methods which are involving the principles of electrochemistry. Hence, they are referred as electrochemical methods. Let me tell you certain examples of metals. You can see here aluminium can, iron nails, silver and gold, bars. If you take up sodium hydroxide, ammonium chloride, potassium chloride, chlorine, bromine, iodine, all these are the various chemicals which are being produced by electrochemical methods. Batteries that we use for making many devices to work, even the fuel cells which convert chemical energy into electrical energy, they are all used on a very large scale, especially in the usage of various instruments as well as devices. So generally the reactions which are carried out electrochemically, if you see, they are having lot of advantages. One of the main advantage is they are energy efficient. They are less polluting. That means obviously they are all very, very eco-friendly. There are the usage of battery in our day-to-day life, the fuel cells that is being utilized, both are involving definitely the principles of electrochemistry for the energy conversions to happen. Energy conversions in many of the batteries that we are using in our day-to-day life is of course involving electrochemistry. So let me just show you all certain examples of certain batteries. You can see here these kind of batteries, you use it for making a clock to function properly so that we are able to manage our time very well. If you want to watch the entertainment media, say the TV, we make utilization of this kind of a remote. And if there are persons who are having the hearing aid which is making them to feel better just because they are able to hear well by using the very small hearing aid, that means that hearing aid which they are using is again containing a very, very small battery. You take up the car is invariably containing huge batteries. You can see the size of the battery is not the same. The battery which we generally use, the cell which we use, in every case if you see, what is the difference between a cell and a battery? A group of cells put together is called as a battery. So, if I am talking about a car battery, the size you can see here, this is Exide battery which has been utilized for making the car run for quite a long distance. If you take up the mobile phones with which the present era is just moving very quickly in terms of communication, the laptops, the toys with which the children play and spend their most of their time invariably are all being utilized only because there are batteries which are inserted into it and making them all function properly. The transmission of the sensory signals, especially through the cells, to the brain and vice versa, as a result of which we are able to carry out the communication properly in between all the cells of our human body. If you take up, they are all having electrochemical origin. You can see here these kind of the nervous system which is involving the transmission of the neurosensory signals. If you see, they are all happening only because of what is called as the principles involving the two energy conversions, as a result of which we are able to easily find out what is happening in the surroundings. The fuel cells, if you take up, they all convert chemical energy into electrical energy, and especially they are used in a large scale in various instruments and devices. For example, the rockets which are all launched by NASA, the hydrogen cell cars, you take up the power backup, they are all involving what is called as hydrogen fuel cell. These kind of electrochemical cells which you have understood that is being utilized in our day-to-day life for various purposes could be of different types. Let me tell you, there are two types of basically the electrochemical cell. One is called as galvanic cell. There are other terms for calling this galvanic cell. It is even called as voltaic cell. And the next variety of the electrochemical cell which you ought to know is electrolytic cell. So let me first show you the pictures of a galvanic cell. You can see here a copper rod, copper plate. If you see here, it is immersed inside copper sulfate solution. You can see a zinc plate immersed in zinc sulfate solution. And here zinc is acting as anode and copper is acting as cathode. Well, these two chambers in which the respective metals are inserted into the solutions are called as the half cells. If zinc is inserted inside zinc sulfate solution, then that particular cell is known as the anode half cell. Whereas if copper plate is inserted inside copper sulfate solution, then that is known as cathode half cell. Of course, these two half cells are interconnected by means of using an porous bridge which is called as salt bridge, which generally allows the movement of ions to happen. Whereas the two metallic plates are to be well connected by means of an electrical wire in a proper circuit manner connected to an electrical bulb. What happens when, if you generally observe, when zinc is immersed in zinc sulfate, copper plate is immersed in copper sulfate solution, well connected by means of a salt bridge, and if the electrical connections are also well set according to this particular diagram, you see after some time, just because of the reactions taking place in this anode half cell as well as this cathode half cell, you find the bulb starts glowing. That means electrical energy is getting generated. Such a kind of an cell which converts chemical energy into electrical energy is of course called as galvanic cell, otherwise also called as voltaic cell. Now, in contrast, if by passing electrical energy you are able to bring about certain chemical reactions, then such a kind of a cell is called as electrolytic cell. if you see here, there is the electrolysis of sodium chloride, the brine solution taking place in a cell which is called as an electrolytic cell. On passing electricity into the aqueous solution of NaCl, you find NaCl, which is in the aqueous medium, is of course getting dissociated into what is called as Na plus ion as well as Cl minus ion. You can see here Na plus is a cation, Cl minus is an anion. So these cations will be moving respectively to the oppositely charged electrode. So if you see, cations will move towards cathode and anions will move towards anode. As a result of which, you will see the chemical change happening in this particular device, which is called as electrolytic cell, or otherwise known as electrolytic device, in which by passing current through an battery, you are bringing about the chemical changes to take place. So generally, if you see in an galvanic cell, I can write as chemical energy is getting converted into electrical energy. If I am talking about an electrolytic cell, I can say electrical energy is bringing about the change into chemical reaction, which I can indirectly make you understand that it is involving chemical energy. So put together, if I say like this, Ce is towards electrical energy in this manner, that means all of them are involving electrochemistry principles. So if you see the signs of the electrodes in both the galvanic cell and the electrolytic cell, they will not be the same. They will be just the opposite. You see here in a galvanic cell, anode will be negative charge, cathode will be positive charge. Let me show you here. Anode is negative charge, cathode is positive charge. But in the case of electrolytic cell, you will find the anode will be positive and cathode will be negative. That is the only main difference between both these galvanic and the electrolytic cell. Now, if we represent the understanding of a galvanic cell and an electrolytic cell in the form of an Venn diagram, which we generally learn in mathematics, let me just tell you, in the intersectional area, you will see some aspects to be common. What are they? One is the utilization of two electrodes, conductive medium, and of course the vessel in which you are carrying it out. Now, in a galvanic cell, it produces electrical current, whereas for an electrolytic cell, you need the power source. Whereas the anode in a galvanic cell is negative, cathode is positive, whereas it is just the opposite in electrolytic cell. You find anode to be positive and cathode to be negative. Of course, there is always the connection to be maintained between the two half cells where oxidation and reduction reactions are taking place in a galvanic cell by means of an porous salt bridge, which will enable the movement of ions to happen. But in an electrolytic cell, there is no need of an salt bridge. So this particular diagram, which is shown to you here, tells you what is common, what are the distinct features of the galvanic cell as well as the electrolytic cell. Daniel cell, if we see, there are of course two electrodes. If we are talking about a Daniel cell involving zinc and copper, then you are going to involve two electrodes, one electrode is made up of zinc, the other is made up of copper, and you try to dip them in the respective salt solution. So I can say zinc is made to be immersed in zinc sulfate and copper is made to be immersed in copper sulfate. Well, the reaction that happens during this kind of a setup of this entire Daniel cell, if you see, the overall reaction is represented as Zn plus copper 2 plus gets converted into Zn2 plus plus copper. That means this zinc, which is existing in the solid state, generally, let me just tell you, appropriately, it should be written like this. That is to the accuracy I mean. Zinc plus copper 2 plus, which is present in the aqueous medium. If you see, it is going to be converted into Zn2 plus. Of course, this is the aqueous, and then copper existing in the solid form. Now, if this zinc rod is immersed in zinc sulfate solution and copper rod immersed in copper sulfate solution, well connected by means of a salt bridge, you will see how the flow of electrons is happening through the outer circuit from zinc anode towards the copper cathode. Let me just erase this particular equation which I have written at the top so that you will be able to understand always the current flow is happening in this direction, whereas the electron flow, if you see, it is happening from the anode to the cathode. That means always the electron flow, you have to understand, is happening opposite to the conventional current flow. So from zinc to copper, the electrons are moving in the outer circuit. Now, if I am going to have a bulb connected over here, then because of the electron flow, I will see the bulb starts glowing. And definitely the current flow is taking place in the opposite direction from the cathode to the anode. This cell, if you take up, it converts the chemical energy that is liberated during the redox reaction into electrical energy and has an electrical potential that can be measured by having an voltmeter connected to the electrical circuit. If you find the value to be exactly equal to 1.1 volt, that means that 1.1 volt will be getting generated only when the concentration of the zinc sulfate and the copper sulfate is equal to what is called as unity. That means indirectly you have to understand the concentration of the ions, especially the zinc 2 plus ions and copper 2 plus ions, is equal to unity. That means the concentration of the solution is expressed in terms of 1 mole per decimeter cube. Such a device is always referred as a galvanic cell, otherwise called as an voltaic cell. Let me show you here. The zinc acting as anode, copper is acting as cathode. You have simultaneously oxidation taking place at the anode, reduction taking place at the cathode, and as a result of which on one half cell you see oxidation and the other half cell you see reduction happening. Put together, the redox reaction taking place resulting in the conversion of the energy. Thereby you can see 1.1 volt that is being generated here, which is called as E of the cell. Electromotive force of the entire cell is equal to 1.1 volt. Now, when you apply an external voltage which is said to be lesser than 1.1 volt, the electrons will start flowing from zinc to copper, and hence the electron will be flowing from zinc to copper means you have to understand the current flow will start taking place obviously from copper to zinc. You can see here e to the base external, if it is said to be less than 1.1 volt, what happens generally is there will be dissolution phenomenon happening at anode and deposition phenomenon happening at the cathode. That means zinc dissolves at anode and copper deposits at cathode. Now, if the external voltage that you are applying is going to be greater than 1.1 volt, then what will happen? Electrons will start flowing from copper to zinc, and the current will flow from zinc to copper. You can see here, zinc is acting as the cathode and copper is acting as the anode here. And the current is flowing in this particular direction from zinc to copper. You can see, whereas the flow of electron is happening in the opposite direction from copper to zinc. Now, during this time, when the external voltage is greater than 1.1 volt, you find deposition phenomenon taking place at the cathode and dissolution phenomenon of copper happening at the anode. Now, when the opposing voltage, that is the external e to the base ext, which is denoting the opposing voltage, if that value reaches exactly equal to 1.1 volt, then what will happen? You will see the reaction stops. There is no further current at all flowing through the cell. I want you to clearly understand, when the E external value happens to be equal to exactly arriving at the value of 1.1 volt, then you see there is no flow of current, no flow of electrons, you will see no chemical reaction. That means chemical energy is not getting converted into electrical energy. This is another example of an galvanic cell. Probably the solution is not involving sulfate ion, but it is involving nitrate ions, NO3 minus. You can see here 1.1 volt shown in the voltmeter, and the flow of electrons happening in the outer circuit from zinc to copper. A galvanic cell is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy. The definitions are very, very important. So let me repeat once again. A galvanic cell, if you take up, it is an electrochemical cell that converts chemical energy of a spontaneous redox reaction into electrical energy. So obviously, whenever there are spontaneous redox reactions happening, it will definitely involve certain changes which are always referred as Gibbs energy change. So especially if you take up the term called as Gibbs energy alone of a spontaneous redox reaction, you will see that is getting gradually converted into certain amount of electrical work. It could be whenever we are using, say for example, for running a motor or any other electrical gadget. For example, if we are using heater or a fan or a geyser, you will see the Gibbs energy of the spontaneous redox reaction getting converted into certain amount of electrical work. Generally, in the case of zinc copper cell, the overall reaction, we write it as zinc plus copper 2 plus getting converted into zinc 2 plus plus copper. You see, actually this particular reaction is summation of the two reactions which are taking place, one at the reduction half reaction taking place at the reduction half cell, and the other which is taking place as oxidation half reaction at the oxidation half cell. Whenever I say oxidation, you have to understand it is involving loss of electrons. So zinc is losing 2 electrons in order to get converted into zinc 2 plus ion. Whereas copper 2 plus is gaining the 2 electrons that is lost in order to become into copper. That means copper has gained 2 electrons, whereas zinc has lost 2 electrons. Now, when I try to add up the two reactions, now let me just put a plus sign here. Now, when I add up the two reactions, well, the two reactions, what are they having something in common? You have to see 2 electrons on the reactant side here and 2 electrons on the product side here. So, let me cancel it because I am just going to add up the two reactions. Well, when I add up these two reactions, the summation of it will arrive at this particular equation. So this reaction is called as net cell reaction. Each half cell, if you take up, it is consisting of a metallic electrode which is dipped into the electrolyte. And the two half cells are connected by means of a metallic wire. Again, you make utilization of a device called as voltmeter, and then you also have an external switch to switch on and switch off. The electrolytes of the two half cells are of course connected internally by means of a salt bridge. When you use this kind of an porous partition U-shaped inverted tube in which enough amount of ammonium chloride or potassium chloride or even agar-agar gel is being completely packed, and if it is kept in contact with the two half cells, you will see definitely the energy conversions happening subsequently, thereby chemical energy getting converted into electrical energy. Why here KCl is written is, please understand, the salt bridge is completely packed with enough amount of potassium chloride. So you can see here zinc rod is immersed in zinc sulfate solution. Copper metallic rod is immersed inside copper sulfate solution. And you know copper sulfate solution, when you dissolve crystals of copper sulfate into water, it turns out to be a blue color solution. So whichever electrode you find the loss of electrons happening, then you say the kind of reaction that is taking place is oxidation. And the other, where gain of electrons is taking place, is of course called as reduction. And if the voltmeter here is showing you the value equal to 1.1, that means that is called as E of the cell, which is always calculated by a very simple formula. Let me tell you, E of any particular cell is calculated by E cathode minus E anode. So, how to represent a particular cell? If I am talking about an zinc copper redox couple, then M slash the ion of M. If I say zinc is immersed in zinc sulfate, then I will write it as, let me just use red color, zinc divided by Zn2 plus. And then put double slash, which indicates the salt bridge. And what is happening in the other half cell? You have copper 2 plus bar copper, and that is equal to 1.1 volt, and denote the flow of electrons like this. This is the notation for the cell representation of involving what is called a zinc copper redox couple. So the two individual reactions which are taking place is copper 2 plus, if you see here, it is gaining 2 electrons in order to become into the metallic copper. And E of copper 2 plus bar copper, that is the reduction potential value of copper 2 plus bar copper, if you see, it is found to be equal to having an value of plus 0.34 volt. Whereas when zinc is undergoing loss of electrons, thereby becoming into zinc 2 plus ion, the reduction potential of zinc is found to be equal to minus 0.76 volt. Now, you are having individually the reduction potential value having obtained because of the reaction taking place in the reduction half cell. You have a potential that is being generated at the oxidation half cell because of the phenomenon of oxidation. Now the question arises, how to calculate E of the cell? Then E of the cell is always calculated by using the formula E of right minus E of left. That means E of right, that means I can even write it in a different manner as E of cathode minus E of anode. So when I take up E of this particular couple, which is a zinc copper couple, let me tell you, E of right is found to be equal to 0.34 volt minus of minus 0.76 volt, because the electrode potential of zinc is minus 0.76 volt. Now let me just do minus into minus, that becomes plus. So if I add up these two and sum it up, I arrive at 4 plus 6 is 10, 1 carry, 3 plus 7, 10, 1 carry. So the value put together is 1.10 volt. Now coming to more examples of other redox couples. Let me take up copper-silver redox couple. In the earlier couple, we saw copper was acting as cathode when compared to zinc, which was acting as anode. But in this case, if you take up, copper will be acting as the anode and silver will act as the cathode. Again, when we are calculating the E cell of this kind of copper-silver redox couple, E right minus E left, then E of this particular redox couple is found to be having a value equal to 0.46 volt. You can see here, copper is acting as the anode here when it is made to be dipped inside copper sulfate solution. Silver is made to be dipped inside silver nitrate solution. And if you see, the voltmeter reading is shown here. It is not equal to 1.1 as it was in the case of zinc copper couple. Here it is 0.46 volt. Obviously here the salt bridge is packed with KNO3. In the previous one we saw KCl. There are KCl, KNO3, NH4Cl, which are all added in order to construct what is called as a salt bridge. The potential of any individual half cell cannot be measured. We can only measure the difference between the two half cell potentials. That generally gives out what is called as EMF of the cell. So generally we can arbitrarily choose one of the potential of the electrode, which is one half cell, and try to utilize this half cell in order to determine the reduction potential of all other half cells. That is what is mentioned in this particular sentence. If we arbitrarily choose potential of one electrode half cell, then that of the other can be easily determined with respect to this. So generally, let me tell you, primarily there are certain reference electrodes which are used in electrochemistry, and one of the primary electrode which is used as primary reference electrode is always called as She electrode. She here means standard hydrogen electrode. It is an electrode which involves the utilization of hydrogen gas subjected at 1 bar into a solution which contains 1 m of hydrogen ion concentration. So you can see here in this particular hood of the glass that is being inserted into the 1m concentration of HCl solution, through which you are already passing hydrogen gas, you will have finely divided platinum which is coated on an platinum foil. Let me just show you elaborate the particular diagram. Hydrogen gas you can see, and here you can see the finely divided platinum, and this is a thin platinum foil. This particular solution is having a concentration of 1 unity of hydrogen ions. That means HCl solution is taken. And these are nothing but the bubbles of hydrogen gas which you are able to see. Now, how are we supposed to represent the She electrode? According to convention, if you take up any particular half cell, especially if we are talking about She electrode, standard hydrogen electrode, then it is represented as, since you are using platinum PT, which is in the solid form, bar hydrogen, where you are allowing the hydrogen gas to pass through, and then again you have to put a slash, because hydrogen gas is made to come in contact with HCl, which is containing H plus ion. So if you see 3 components, the platinum coming in contact with hydrogen gas, and then that in turn coming in contact with H plus. So you always denote even the state of matter. Platinum is in the solidified state, hydrogen is existing in the gaseous form, whereas here H plus is present in the aqueous medium. Now this particular She electrode is assigned an value of 0 potential at all temperatures, corresponding to a particular reaction which is happening, where H plus is gaining 1 electron in order to become what is called as atomic hydrogen. If I say half of H2, it is nothing but equal to just H. This particular standard hydrogen electrode, if you see the construction, it consists of an platinum electrode which is coated with a thin layer of platinum black. And that particular electrode is dipped inside an acidic solution which is generally HCl, and you will allow pure hydrogen gas to be bubbled through it. Immediately if you see, the hydrogen gas bubbles coming in contact with H. At that particular time, the concentration of both the reduced and the oxidized forms of hydrogen is maintained at unity. This implies that the pressure of the hydrogen gas is 1 bar, and the concentration of hydrogen ion in the concentration is obviously equal to 1 molar, which means 1m. So how are we supposed to represent the entire She electrode? You can see here platinum coming in contact with hydrogen, gas which is at 1 bar subjected, and then H plus ion, aqueous solution of 1m. If I am going to connect the She electrode to an unknown electrode, or I would say here not an unknown electrode, because I have denoted here, if I would have denoted here as m, n plus bar m, then it is unknown, but here it is clearly given as zinc. That means here I should understand She electrode has been coupled with zinc. Now here you can see Zn2 plus. Again the concentration of zinc ion is said to be equal to 1m, and zinc rod is immersed inside what is called as zinc ion solution whose concentration is equal to 1m. Let me show you here. You can see zinc is immersed inside zinc nitrate solution. Same way here you can see She electrode through which hydrogen gas is passed. You have here a platinum strip. You can see the hydrogen gas bubbles coming up, and the bottom part you have an platinum strip here. So this particular setup you see here, the She electrode has been clubbed with zinc electrode. Now when such a kind of a setup is done, zinc here is acting as anode and She is acting as cathode. Now what is the EMF that is being noted in the voltmeter? It is equal to how much? 0.76. So let me just tell you here, when I calculate E of the cell is equal to what? I write the formula as E cathode minus E anode. Now the EMF of the entire cell, how much has it been determined? In the voltmeter reading you are able to see it is equal to 0.76. That means 0.76 is equal to, what is E cathode value? E cathode value is, because the electrode which is used here as a cathode is She electrode, and just now we have understood that whenever we are talking about the electrode potential of She electrode, it is arbitrarily taken to be having a value equal to 0. That means, what is E of anode? E of zinc 2 plus bar zinc. Now that means E of zinc 2 plus bar zinc, if I am trying to take this to this side, that becomes positive. Is it not necessary for me to bring 0.76 to this side? That means the value becomes equal to minus 0.76 volt. 0.76 volt. Let me use the eraser so that you are not getting confused. 0.76 volt. This is how, with the help of She electrode as a primary reference electrode, we are able to determine the electrode potential of all other electrodes. This is surely going to be definitely asked for an 5-mark question. So draw the diagram, write the representation, and then give the explanation and do this calculation so that you are not going to miss out the entire allotment of the marks given for that particular question. Now let us look into a very, very important derivation which is known as Nernst equation in electrochemistry. Nernst, if you take up, he showed that for any kind of an electrode reaction, especially the reduction half cell reaction, wherein a metal is able to undergo gain of electrons, thereby getting reduced into the respective metal, the equation is represented in a very short scientific manner as Mn plus is gaining n number of electrons in order to become M. Obviously, whenever I talk about M, I should denote S as the subscript. AQ should be, obviously, let me write this equation more correctly. I can write M, N plus, and then like this, aqueous at the bottom. Then you write N electrons, it is gaining. Then it is becoming into M, which is in the solid state. So please understand, all these are actually in the subscript. The electrode potential at any concentration, if it is measured with respect to She electrode, then how is the representation done? E of electrode potential of Mn plus bar M is equal to E naught value minus RT by NF into Ln, logarithm to the base E, M divided by Mn plus. Now what is this M? This represents the concentration of the metal in the solid state. What is Mn plus? It represents the concentration of the respective metal ion. Now, whenever we are talking about the concentration of a metal which is existing in the solid state, we know it is always equated to unity. That means E of, let me tell you, E of Mn plus bar M is equal to E naught of Mn plus bar M minus RT by NF into ln. In the numerator, I can just substitute the value of 1 because the metal is existing in the pure state. Activity is equal to 1. Now, in the Daniell cell, the electrode potential for any given concentration of copper 2 plus and zinc ions, if we see, we can write as the separate equation involving at the cathode and separate equation which is involving at the anode. If I say for cathode, it is E of copper 2 plus bar copper, then that is equal to E naught. Please always remember E naught, wherever it is e to the power 0, it represents the electrode potential determination at standard conditions of temperature and pressure. Now, E naught value of copper reduction potential minus RT by NF into 1 divided by copper 2 plus. When it comes to the case of the electrode potential of zinc, then the expression is equal to E naught Zn2 plus bar Zn minus RT by NF into ln 1 divided by Zn2 plus. Now, what are we supposed to do next? E cell we are supposed to calculate, which is the formula E cathode minus E anode. So, you are supposed to sum up these two equations right now. So, on summing up, you will see for this kind of a Daniell cell, the cell potential is always represented as E of cathode minus E of anode. Now, E of a cell is equal to E naught of a cell minus RT by NF ln of Q. Now, what is Q? It is very simple. It is reaction quotient. Here in this zinc copper couple, Q is equal to Zn2 plus concentration divided by copper 2 plus concentration. Now, E cell is equal to E naught cell minus RT by NF into ln. In the place of Q, let me substitute the concentration of Zn2 plus divided by copper 2 plus. Now, well, I can even write this equation in a different manner. I can write as E of cell is equal to E naught of the cell plus RT by NF into ln of concentration of copper 2 plus ion divided by Zn2 plus ion. Now, you must be wondering how Q is equal to Zn2 plus bar copper 2 plus. Because while we had discussed about the Daniell cell representation, you have understood the cell net cell equation. It was involving Zn2 plus copper 2 plus in the aqueous solution gives rise to Zn2 plus copper. Now, without fail, you are supposed to write aqueous here, without fail, yes. Now, Q means generally, let me tell you, Q means it is equal to the ratio of the concentration of the products Zn2 plus and copper divided by Zn into copper 2 plus. But you know that these activity or the concentration of zinc and copper, they are in the solid state, existing in the pure state. So, the values are equal to 1. So, I will simply substitute and arrive at, which is equal to, I am just writing in a different color. I will just write here, red color. That means Q becomes equal to just Zn2 plus divided by copper 2 plus. That's all. And you are supposed to put square brackets because you are talking about always the concentration here. So, with that, Nernst equation, which is very, very important in electrochemistry, has been dealt. So hope you have understood all about the introduction concepts of electrochemistry. Where are we using electrochemistry? Of course, what are the various kinds of electrochemical cells and what is meant by a galvanic cell, how is it constructed, and also the primary reference electrode, which is She electrode, and how can we determine the electrode potential of any particular electrode when compared with an She electrode, and complete setup if it is done. Is it possible for us to easily determine any unknown electrode potential by using She? Definitely the answer is yes. Hope to see you in the next class with more concepts of electrochemistry.